सेंट्रल ऑर्बिट। सेंट्रल ऑर्बिट टॉपिक पढ़ने से पहले हमें पता होना चाहिए कि सेंट्रल फोर्स क्या होता है। अ फोर्स विच इज ऑलवेज डायरेक्टेड टुवर्ड्स अ फिक्स्ड पॉइंट इज नोन एज अ सेंट्रल फोर्स। मतलब कि एक ऐसी फोर्स जो कि किसी फिक्स्ड पॉइंट में हमेशा की डायरेक्ट होती है उसे कहते हैं सेंट्रल फोर्स, और फिक्स्ड पॉइंट जो होता है उसे हम लोग कहते हैं सेंटर ऑफ फोर्स। फिर हम लोग करेंगे कि सेंट्रल ऑर्बिट इज अ प्लेन कर्व। हमें बताना है कि सेंट्रल ऑर्बिट एक प्लेन कर्व होता है। In this diagram, we can see there's the point O, A. Let the particle moves under a central force MP. There, MP is the central force, and the particle is moving under a central force MP with O at its center. The force acting along the AO, which is acting along the AO, the force is acting along AO, then the equation of the motion will be M d square r by dt square is equal to minus MP. The force is acting along the radius vector minus r, then r cross d square r by dt square equal to 0, r cross d square r by dt square plus dr by dt into dr by dt is equal to 0. We can write it as d by dt r cross dr by dt is equal to 0. Then when we integrate this expression, we get the c, where c we define as any constant vector. Now there is a differential equation of a central orbit. There are two types of differential equation of central orbit. First is the plane form of the equation. In this diagram we can see that there is a particle. Let the particle be at A. There is this a particle which is at A distance r comma theta at any time t. Point O, there which is the pole, is the center of the force, and the acceleration p acts along the AO, which the acceleration is acting along the point AO. Then d square r by dt square minus r d theta by dt का whole square is equal to minus p. Ra means the radial acceleration, which will be equal to r minus r theta square. Let us assume this as equation number 1, and 1 upon r d by dt r square d theta by dt is 0. Now, after integrating, we have r square d theta by dt which is equal to h. Putting r equal to 1 by u and differentiating with respect to t, we get dr by dt which is equal to minus 1 upon u square. Differentiating r with respect to t, we get minus 1 upon u square du by dt, which will be minus 1 upon u square du by dt. We can write as du by d theta into d theta by dt equal to minus r square d theta by dt dot du by d theta, which is equal to minus h du by d theta, as r d square by d theta is equal to h. Putting the value of r d square by d theta is equal to h, we get minus h du by d theta. Is it okay? Then after differentiating with respect to t, we get d square r by dt square equal to minus h d square u by d theta square d theta by dt, which will be equal to minus h d square u by d theta square dot h u square, which will be equal to minus h square u square d square u by d theta square. Then putting the values of d square r by dt square and d theta by dt, we get minus h square u square d square u d theta square minus 1 upon u h square u to the power 4, which is equal to minus p. H square u square d square u d theta square plus u equal to p. This is the polar form of the equation. Now the next is the pedal form of the equation. Pedal form of the equation. Let us consider small p be the length of a perpendicular from pole to the tangent at point A, which is r comma theta, and OB is equal to p. Then 1 upon p square will be equal to 1 upon r square plus 1 upon r to the power 4 dr by d theta ka whole square. 1 upon p square will be is equal to u square, because r equal to 1 by u. We can see that r equal to 1 upon u, and therefore 1 upon r square will be equal to the u square plus du by d theta ka whole square. Differentiating it with respect to the theta, we get minus 2 upon p cube dp by d theta, which is equal to 2 du by d theta plus 2 du d theta dot d square u by d theta square. Then minus 1 upon p cube dp by d theta, which is equal to du by d theta d square u d theta square plus u. Minus 1 upon p cube dp will be equal to p upon h square u square du. Minus 1 upon p cube dp will be equal to minus 1 upon r square dr, p by h square equal to r square, and h square upon p cube dr by dp by dr equal to p. This is the Poidal form of the equation. So first we learn what is the central orbit, then central orbit in a plane curve, then differential equation of central orbit. Two types है, polar form of the equation है, and the pedal form of the equation. Now we will learn about what is a motion on a plane curve. In this, let us suppose the position of the particle on the curve at any time t bp x comma y with arc length as s, we can see the s, measured from a fixed point p1. Let v be the velocity at point p and x comma y are the components, and x comma y are the components of the force acting along the coordinate axis. On resolving the forces along the tangent at P, the motion is mv dv by ds equal to x cos phi plus y sin psi. Cos psi is dx by ds and sin psi is dy by ds. mv dv by ds, putting the values of cos and sin, we get x dx by ds plus y dy by ds. Now we integrate with respect to s. The mv dv by ds equal to integration x dx by ds plus y dy by ds plus c1, where c1 is any arbitrary constant. 1 by 2 mv square will be equal to x dx plus y dy plus c1. Half mv square will be equal to x dx plus y dy plus c1. Now let us take x dx plus y dy is equal to phi x comma y. X will be del phi by del x and y will be del phi by del y. Then half mv square, again putting the values of x and y in this equation, we get half mv square integrating del phi by del x dx plus del phi by del y dy plus c1. Del phi plus c1, which will be equal to half mv square phi x comma y c1. Here phi x comma y is known as the work function, and half mv square gives the kinetic energy, which means that half phi x comma y is called the work function and half mv square is known as the kinetic energy. Now let initially the particle of mass m starts the motion with velocity v naught from the point p1, x naught and y naught are the points. Then half m v naught square is equal to phi x naught y naught plus c1. Half m v square minus v naught square will be equal to phi x comma y minus phi x naught comma y naught. This is the motion on a plane curve. The next topic is Kepler's laws of motion. Kepler gives the three laws of its motion. First is each planet describes an ellipse having the sun in one of its foci, which means that हर एक planet ellipse के elliptical orbit में rotate करता है जिसका sun उसका एक foci होता है. Second law is the radius vector drawn from the sun to the planet describes equal areas in equal time. Means जो radius vector है जो कि sun to the planet में है वो describe करता है हमारा equal area और equal time में. Third law is the square of the periodic time of the various planets are proportional to the cubes of the major axis of the orbit, t equal to 2 pi under root mu a3 by 2, where mu is the constant. This is the third law of Kepler and this formula is t is equal to 2 pi under root mu a to the power 3 by 2. Now here's one numerical. Question is, a particle describes an ellipse under a force mu upon r square and has a velocity v at a distance r from the center of the force. Then we have to show that its periodic time is 2 pi under root mu 2 upon r minus v square by mu power minus 3 by 2. We know that for the ellipse we have v square equal to mu 2 upon r minus 1 upon a. V square by u will be equal to 2 upon r minus 1 by a. Then the value of 1 by a will be 2 by r minus v square by mu. Then time period will be equal to 2 pi under root mu a to the power 3 by 2. This is the Kepler's laws of motion. Kepler defined the three laws. First is each planet describes an ellipse having the sun in the one of its orbit. Second is the radius vector drawn from the sun to the planet describe equal areas in equal time. And the third is square of the periodic time of the various planets are proportional to the cubes of the major axis of the orbit, which will be formula is t is equal to 2 pi by under root mu a to the power 3 by 2, where mu is defined as any constant.